For today's lesson, we are going to be talking about solving inequalities. So we are going to talk about absolute value inequalities, how we go about solving those, how it might be similar to solving absolute value equations. So when you solve absolute value equations, you are going to solve using two inequalities just like you use two equations when you're solving an absolute value equation. Now in the first inequality, the inequality will stay the exact same, just without the absolute values. And in the second inequality, you take the right-hand side and you make it the opposite, you make it negative, and you also switch the direction of the sign. So if it was a less than sign, it becomes greater than. If it was a greater than or equal to sign, it changes to less than or equal to. So take a look at example 1. We have the absolute value of x minus 5 is less than 2. So we write two inequalities. The first one is the exact same thing, just without the absolute value signs. So that would be x minus 5 is less than 2. And then for the second inequality, you make the right-hand side negative, and then you switch the inequality symbol. So this would be x minus 5 is greater than negative 2. All right, for our next step, we are going to go ahead and solve each of these inequalities. So add 5 to both sides. In both cases, we end up with x is less than 7. And in the second one, we have x is greater than 3. Now you may remember this from Algebra 2. With absolute value inequalities, this is going to be either an and or an or statement. And in order to figure out what that is, you can start with the original equation. And if you see that it's an absolute value is less than a number, it's going to be a conjunction. It's going to be an and statement. If, on the other hand, it's the absolute value is greater than the other side, then this is going to be a disjunction or an or statement. In this case, we have a less than, so this is going to be a conjunction. This is an and statement. So your value of x has to be less than 7 and greater than 3. Now if we write this in interval notation, that would be parentheses 3, 7. Let's take a look at another example. We have 3x minus 7 in absolute values is greater than or equal to 11. All right, we'll start the same way. We'll write two inequalities. So 3x minus 7 is greater than or equal to 11. 3x minus 7 is less than or equal to negative 11. And then we'll solve each inequality. So we'll add 7 and then divide by 3. That gives us x is greater than or equal to 6 here. For the second inequality, adding 7 and dividing by 3 gives us negative 4/3. Now if you look back at the original inequality, the absolute value was greater than or equal to the right-hand side. That means that this is going to be a disjunction or an or statement. So that means we have two pieces, right? Either x is greater than or equal to 6, or x is less than or equal to negative 4/3. It can't be both, but all your solutions are going to be in one of those two intervals. So to write this in interval notation, we're going to write each interval on its own, and we'll attach it together using a union symbol. So x is greater than or equal to 6. That means that x can be equal to 6 or anything bigger than it. So from 6 to infinity with a square bracket on 6. And then we use our union bracket, and for our second part, x is less than or equal to negative 4/3. That means it could equal negative 4/3 or anything less than that. So it can be anything from negative infinity to negative 4/3, including negative 4/3. So we have a square bracket on the negative 4/3. And that is your solution set for this example. Now there are some special cases. For example, look at this first one. The absolute value of x squared plus 2x minus 5 is less than negative 2. Now before you start writing out, okay, I know I have to write two inequalities, write them all out, and then start trying to solve them, take a step back and look at what this is saying. This is saying that whatever expression you get on the left, and you take the absolute value of that, is going to be less than -2. Now we know an absolute value, once you take the absolute value of anything, it's always going to be either 0 or positive. Is there any chance that it could be negative? Well, no. Well then, can this expression ever be less than -2? No. So there's no need to actually go about solving for x because I know there's no value of x that will make this inequality true. So for this, we would say there are no solutions. You can also say it's the empty set. And this is how we denote the empty set. Now, if you look at the second one, we have the absolute value of 4x minus 10 is greater than or equal to -3. Now again, we remember that anything that's inside the absolute value, once you take the absolute value, is only going to ever equal 0 or positive. So when is that going to be greater than or equal to -3? Well, no matter what x is, you're going to get some number that's 0 or positive, which will always be greater than or equal to -3. So in this case, well, what is x going to be? X can be anything. No matter what x is, if you multiply by 4, subtract 10, and then take the absolute value, it's going to be greater than or equal to -3. So your solution here is just all real numbers. You can use the all real numbers symbol there. Now let's move on to polynomial inequalities. So when you have a polynomial, you know that the only places where the value of that polynomial will change from positive to negative is at the zeros. In other words, at the x-intercepts, those are the only places where it can actually change from positive to negative. It doesn't always change from positive to negative. Sometimes it could bounce right back down, but the only places where it can possibly change would be at those zeros. And so in order to solve polynomial inequalities, we are going to have to first start by finding all the zeros. These are what we are going to call critical values. Once you've done that, then you're going to determine the general shape of the graph in order to determine the intervals that are positive and negative. So to determine the general shape of the graph, if you know it's a quadratic, then you know it's a parabola. And then figure out, okay, it's a parabola, which way does it face? And get the general shape. If it's not quadratic, if it's a higher degree polynomial, then you'll have to use what you know about higher degree polynomials in graphing. So you'll have to figure out, okay, does it bounce or cross at this specific zero? What is the end behavior on either side of the graph? So here, for example, we have this parabola on the right. And what you'll end up determining is, okay, I know that here and here, up at the top, those values are positive. All the values that are above those zeros, above the x-axis, that's where it's going to be positive. Anything below, which is the center of that parabola, is negative. And so that will help us when we talk about polynomial inequalities when you're asked to find where is this greater than 0, or where is this less than or equal to 0. And so once you have your graph, you can easily determine where that polynomial is positive or negative. Here's an example. We have 2x squared plus 5x is greater than 12. So first thing, you want to move everything over to the left-hand side, so we'll subtract the 12 over. And now let's see if this is factorable. It's a quadratic. Splitting the middle, we're able to factor this. So it ends up factoring to be 2x minus 3 and x plus 4. And now you set this equal to 0 just to find where the critical values are. Okay, just to find where the roots of this function, where the zeros of this function are. So that would be at -4 and 3/2. Now we have to sketch the general shape of the graph. Because we know it's x squared, we know it's a parabola, it's a quadratic. So it's a parabola that's facing upwards. Why upwards? Because we have a positive leading coefficient. and we know where it crosses the x-axis. So the general shape is, well, it goes through -4, and it goes through 3/2, and it's a parabola facing upwards. Now, looking back at the inequality, we had 2x squared plus 5x minus 12 is greater than 0. Where is this function greater than 0? Well, in this section here and this section here. And so now we just have to write down those intervals into interval notation. So that first interval, the one here, that means that x can be anything from -infinity all the way up to -4, not including -4, because at -4 it's actually equal to 0. We want it to be greater than 0. So we would say from -infinity to -4. And then for the second part of the graph, on the right there, that's above the x-axis, that's our second interval where it's greater than 0. So starting from 3/2 all the way to infinity. Again, we don't include 3/2 because at 3/2 it is exactly equal to 0, and we want everything that's only greater than 0. And those are the two intervals where we have a solution x that will satisfy this inequality. Let's do one more example. X cubed minus 4x squared minus 9x plus 36 is less than or equal to 0. Let's start by factoring if we can. It looks like we have 4 terms here. We can try factoring by grouping. Factoring by grouping gives us x squared times x minus 4, and then minus 9 times x minus 4, less than or equal to 0. And then now we can write this as x squared minus 9 times x minus 4. And then that x squared minus 9 we can factor out even further using difference of squares. And that would be x plus 3x minus 3. And now we are going to write down what our critical values are, where our x-intercepts are. So that would be at -3, 3, and 4. So now drawing the general shape of the graph, we're going to have zeros at -3, at 3, and at 4. Now comes the trickier part. This is a polynomial of degree 3. That's an odd degree. And we have a positive leading coefficient. That means that the end behavior on either side of this graph is going to be down on the left side and up on the right-hand side. Also, we know that the multiplicity for each of these intercepts is 1, which means at each intercept, our graph is going to cross right through that root. So here's a general shape of the graph. Again, the important thing here is that we can identify the parts that are above and below the x-axis. In this case, our polynomial inequality was less than or equal to 0. So we're looking at the places where it is below or equal to the x-axis. So that would be this section right here and this section right here. So that's negative there and that's negative there. Because it's less than or equal to, we want to also include -3, 3, and 4. So for the first interval there, our interval extends from -infinity all the way to -3, and we want to include -3. For our second interval, that goes from 3 to 4, and we want to include both 3 and 4. So we'll use the union symbol here, and then put square brackets on 3, 4. All right, so now let's talk about some what we might call unusual solution sets when it comes to these polynomial inequalities. So here's the first one. X squared plus 2x plus 4 is greater than 0. Now x squared plus 2x plus 4 is a quadratic, it's a parabola facing upwards, and the entire thing is above the x-axis. So for that, where is it greater than 0? Well, the whole thing is greater than 0. So in this case, we would say that our solution set is from negative infinity to infinity, or you can say all real numbers. In this next one, x squared plus 2x plus 1 is less than or equal to 0. This is a parabola that just touches the x-axis at its vertex. So in this case, where is it less than or equal to 0? Well, it's not less than 0 anywhere, but it is equal to 0 right at that vertex. So this is an example where you just have a single point for a solution. In the next one, we have x squared plus 3x plus 5 is less than 0. So this is a parabola facing upwards. The entire thing is above the x-axis. So where is that less than 0? Where is that negative? Well, there's nowhere where that is negative. So we would say this has no solutions. You can also say it's the empty set. Okay, and in our last case, we have x squared minus 4x plus 4 greater than 0. And this is a parabola whose vertex just touches the x-axis. So where in this case is this parabola greater than 0? Well, it's greater than 0 almost everywhere, with the exception of that one point where it's equal to 0. It's not greater than 0. So in this case, you would say your solution set is everything from negative infinity all the way up to the vertex, which is at 2. So from negative infinity all the way up to 2, and then from 2 all the way to infinity. And those are the 4 types of what you might consider more unusual solution sets, but that's the general idea when it comes to solving a polynomial inequality.